Hello there! This lecture is all about ANOVA, or analysis of variance. And analysis simply means to break down into components. And then variance just refers to separating the variance, or differences, and the dependent variable that's due to the independent variable from the variance, or differences, and the dependent variable that are just due to random chance or sampling error. So kind of the same thing you've been doing all along, comparing the observed differences to the differences that you would expect to see just due to random chance. So this lecture is only going to cover the basic one-way analysis of variance, meaning that we only have one factor or independent variable. The word factor and independent variable can be used synonymously with each other. So if somebody says a factor, they're talking about an independent variable. If they say independent variable, it's the same thing as saying a factor. So for our purposes, we're only working with one factor or one independent variable. But we have two or more levels of that independent variable. So for example, let's say we want to compare benevolent sexism perceptions across different sexual orientations. So we have a single factor, sexual orientation. That's our single independent variable. It's actually a quasi-independent variable because we can't manipulate sexual orientation. They come to us that way. So we have one factor, sexual orientation, and our dependent variable is benevolent sexism perceptions. But within that one factor, that one independent, quasi-independent variable, we have four different levels. So let's say we're comparing benevolent sexism perceptions, our dependent variable, across heterosexuals, gay males, lesbians, and bisexuals. So we have four different levels of sexual orientation for that one independent variable, which is sexual orientation. Well, here's another example of a one-way analysis of variance scenario. Let's say you want to compare the effectiveness of pain relief drugs on pain intensity. So pain relief drugs would be our independent variable, our factor. Only one of them, right? Just looking at pain relief drugs. Pain intensity would be our dependent variable. But let's say that we have three different levels of pain relief drugs, or three different levels of our independent variable. Morphine, fentanyl, and then another group who gets like a placebo, like a sugar pill, a control group. So in that case, we have three levels of pain relief drugs. Now, it's important to note that each different level of the independent variable gets assigned to separate groups. So for instance, in the pain relief drugs example, you take a random sample, you split it randomly into three different groups. One group gets morphine, one group gets fentanyl, the other group gets a sugar pill, and then you measure their the pain intensity after the fact, after they receive the drug. So in the next lecture, you're going to learn about two-factor analysis of variance. So this is when you use an ANOVA to examine the impact of multiple factors or multiple independent variables. So again, that'll be covered in another lecture. But just to give you a preview, maybe instead of just looking at the effect of pain relief drugs on pain intensity, you want to look at the effect of pain relief drugs on pain intensity among different types of pain. So maybe you could compare the effectiveness of morphine and fentanyl on pain intensity for arthritis patients, fibromyalgia patients, and multiple sclerosis patients. So in this example, you have two factors, right? You have the drug, morphine or fentanyl, two levels of your drug. You also have the type of pain. So this would be a quasi-independent variable. So you'd have arthritis, fibromyalgia, and multiple sclerosis. So three levels of that quasi-independent variable. That's a basis of comparison for your dependent variable or pain intensity, but isn't being directly manipulated by the researcher. Here's another example. Maybe you want to examine the impact of commercial volume, so soft, medium, or loud volume, on persuasion for males and females. So you would have two factors, volume, three levels of that factor, soft, medium, or loud volume, and then sex would be your quasi-independent variable in that case, two levels of that, being male or female, and then your dependent variable would be persuasion. So with the more sophisticated analysis of variance that's beyond the scope of this lecture, but the two-way factor, or the two-way or the two-factor ANOVA, you can examine main effects, so the effects of each independent variable on the dependent variable, and you can examine interaction effects, so how the two independent variables interact to have an effect on the dependent variable. So with the two-factor ANOVA, you could ask questions like, are certain pain medications more effective for different types of pain? Or does the effect of commercial volume on persuasion depend on the sex of the person watching the commercial? So I just want to give you a preview of two-factor ANOVA, but for now, let's focus on a single independent variable that can have however many levels that you want. All right. So this lecture will start off with the difference and similarities between t-tests, something you already know a lot about, and then what we're moving on to, analysis of variance. Then I'll get into what is between and within group differences. So both of these are used to compute this thing called the F statistic in step 3 of your hypothesis test, which is the statistic that we'll be computing with our data for the analysis of variance. And as you'll see, the between and within group differences are similar to the observed and the observed differences between means and the differences you'd expect to see due to chance or the standard error from t. Then we'll move on to the F distribution. So we're no longer going to be looking at the t distribution when we're finding our critical values. We're moving on from t, going to F. And the F distribution is different from the distributions that we've been looking at before, and I'll explain why. Statistical notation and computing the F statistic will follow the F distribution. So I will just show you some new symbols that we're going to be working with, what those symbols represent, and then the basic calculations for step 3 of the analysis of variance hypothesis test. So how to figure out this F observed value. Then I'll go into the other steps of the hypothesis test. So we're going to focus on step 3 for a little bit, and then I'll talk about step 1, stating the hypothesis, step 2, determining the critical value for the hypothesis, and then step 4, making your decision, right? Reject or fail to reject the null, and then stating your conclusion for the ANOVA. Then with ANOVA, if you have a significant finding, not only do you want to figure out the effect size, but you need to do a Tukey's HSD post hoc analysis. So when you have a significant ANOVA, all that tells you is that there is a difference between at least one pair of the groups. So a difference in the dependent variable based on at least one level of the independent variable. But you don't know which groups are significantly different. This post hoc analysis will help you determine which groups are significantly different. And then finally, in the next lecture video, I will do 2 examples of an ANOVA hypothesis test where I calculate the effect size and do Tukey's HSD post hoc analysis. And if you're curious what HSD stands for, it stands for honestly significant difference. Honest. All right. So both the t-test for single samples and the t-test for independent samples, or independent measures, and the analysis of variance examine mean differences in the dependent variable at a single time period after manipulating the independent variable. So we're measuring our dependent variable after we manipulate the independent variable to test hypotheses about the population from which the sample was originally drawn. So if findings are significant, or in other words, we reject the null hypothesis, then the researcher can be fairly confident that the observed differences in the dependent variable, whatever we're measuring, are due to the independent variable, whatever we manipulated. And if everyone in the population received the same treatment, or the independent variable, there would be a similar effect on the dependent variable for everyone. So when you find that something is statistically significant, we know that it's highly unlikely that we got that result due to chance, which means it's pretty likely that we got that result because the independent variable had an effect on the dependent variable. Therefore, we're pretty confident that if we did the same thing to everybody in the population, if we manipulated that independent variable for everybody that we're interested in, not just our sample, we would see a similar result. Now the t-test for the single sample. This is when you just have one level of the independent variable. And this involves testing a hypothesis about a single population mean that's implied by a single sample. So remember, in inferential statistics, we don't really care about the sample in of itself. We're just using that sample as a proxy for the population. That's why when you state your hypothesis in symbols, you use mu, back in the day when we were doing t. Now we're beyond that. But you used mu instead of m. Right? Because we're just saying, based on this sample, what we expect to see in the population. Okay, so for a t-test for single samples, here's an example of that. So maybe your alternative hypothesis, what you expect, is that on-the-job training significantly improves performance. So you could test the effectiveness of on-the-job training by taking a single sample from the population of employees, give them on-the-job training, and then a week later, give each employee in the sample a performance appraisal, and to see if the sample's mean performance appraisal score is significantly higher than the population mean performance appraisal score, right? Those who didn't receive the training. Or in other words, if you find that it's significant, that means that there's a very low probability that their sample mean would have occurred due to random chance, even if the null hypothesis was true and on-the-job training did not improve performance. So, if that sample mean is significantly higher, if there's a really low probability that you observed that difference due to chance, then you can be confident that on-the-job training would improve performance for all employees in the population. So that's an example of a T single sample type of research scenario. Then there's the T independent measures or independent samples scenario. So this is when you have two levels of your independent variable. So let's say that you want to test a hypothesis about the difference between two population means implied by two samples. So maybe you want to see if on-the-job training from a peer has a significantly stronger effect on improved performance than on-the-job training from a supervisor. So we have two different levels of training: on-the-job training from a peer and on-the-job training from a supervisor. And again, under our alternative hypothesis, we think that on-the-job training from a peer will be better. So we could test the effectiveness of on-the-job training from a peer versus on-the-job training from a supervisor by taking a single sample from the population of employees, and then a randomly assigned half of those employees from our sample gets on-the-job training from a supervisor, and then the other half of our sample receives on-the-job training from a peer. Then, a week after receiving the training, we give the entire sample a performance appraisal, and we see if the group who received on-the-job training from a peer has a mean performance appraisal score that is significantly higher than the mean from the group who received on-the-job training from a supervisor. And if we find that that is significant, then we know there's a very low probability that their sample mean difference would have occurred due to random chance, even if the null hypothesis was true and on-the-job training from a peer was not more effective than on-the-job training from a supervisor. So if we find that there's a significant finding, highly unlikely, low probability that we would observe this result just due to chance, so it's probably due to the fact that on-the-job training from a peer works better than on-the-job training from a supervisor. So in other words, if the sample with on-the-job training from a peer has a significantly higher performance appraisal score compared to the sample with on-the-job training from a supervisor, then you'd be pretty confident that on-the-job training from a peer would be superior for employees in the population. Again, we're using our sample as a proxy for the population. We only care about what happens in the sample because that tells us what would probably happen if we did what we did in our sample to everybody in the population. Well, now we're moving on to ANOVA. And this is where we have two or more levels of the independent variable. So if you're testing a hypothesis about the difference between two or more population means. So you start by looking for any difference, right? You do the analysis of variance, and then you do the follow-up tests to look to see which groups have significantly higher or lower means using that post hoc analysis. So here's an example of an ANOVA scenario. Let's say that your alternative hypothesis is that there's a significant difference in performance appraisals based on receiving on-the-job training from a peer, on-the-job training from a supervisor, video-based training, or no training at all. So now we have four levels of that independent variable. So we would have to do an analysis of variance. So this would be the same process as the T independent measures, but you would randomly divide the sample into 4 groups instead of 2 groups, and each group would get one of the trainings being tested, with, one group getting no training at all. Here, if the findings are significant, then you know that the differences in performance between the groups who received the different types of training far exceeds the random differences within the groups who received the same training. So if you found significant results, then you would be confident that the different types of training would have different effects on performance among all employees. And you would do a post hoc analysis to see which types of training are significantly better. Now, it's important to note that you can use an analysis of variance or t-independent measures when you have two levels of the independent variable, or in other words, two groups. But do not simply do multiple t-tests for independent measures when you have more than two groups. When you have more than two groups, or in other words, more than two conditions, or more than two levels of the independent variable, you must do an ANOVA, not a bunch of t-tests for independent measures. So this is because each statistical test has a certain degree of type 1 error. And remember, the probability of type 1 error is equal to your alpha level, right? So the alpha level is telling you how extreme your test statistic needs to be considered significant. And remember, that test statistic sometimes can be extreme even if your independent variable has no effect, and that would result in a type 1 error because you would reject the null and say that the findings were significant when in fact they weren't. All right, so remember, each statistical test has a certain degree of type 1 error. So, with each statistical test you run, there's some risk of rejecting the null hypothesis when the observed differences between means was actually a fluke, just due to random chance and not the independent variable. So if you do multiple t-tests, you're inflating that risk of type 1 error, or rejecting the null incorrectly, with each test. With ANOVA, you have a single omnibus test. Omnibus just means you're examining everything at once. So you have a single test with ANOVA that examines multiple groups and a single statistical analysis with a fixed probability of type 1 error. It's equal to your alpha level. Whereas if you do multiple t-tests, each t-test has its own type 1 error and you're just kind of multiplying it up with all those multiple t-tests. So in short, we use ANOVA instead of multiple t-tests to avoid an increased chance of making a type 1 error. And that's an important concept to understand. So a little bit more about T versus F, or t-test versus ANOVA. So both the T and the F compare actual sample mean differences to the differences expected just due to chance if the independent variable has no effect, or in other words, the null hypothesis is true. Remember, we use ANOVA when we have two or more groups. Now, when you have more than two groups, it's impossible to calculate a mean difference, right? You can calculate a mean difference with two means, right? Just mean 1 minus mean 2. But you can't calculate a mean difference when you have more than two groups. So for ANOVA, variance is used to represent the size of mean differences between two or more samples. We're no longer just going to find mean differences, we are going to use the variance as a measure of those differences between multiple groups. So when you calculate the F statistic, and I'll show you the numeric calculations for this, but conceptually, we are just comparing the overall differences between treatment conditions, or between groups, or between levels of our independent variable, to the differences within each condition, or the differences within each group or independent variable, within each level. So conditions, groups, levels, that's all referring to the same thing. So let me get into the nitty-gritty about what contributes to the differences between groups, our numerator of F, and what contributes to the differences within groups, or the denominator of our F statistic. So between levels variability, or between groups differences, can be due to the independent variable and due to error. So the independent variable refers to the treatment effect, and this is what we hope the differences are due to, right? We hope that the differences in the dependent variable among the different levels of the independent variable is due to the fact that each different group is receiving a different level of the independent variable. In addition to differences resulting from the independent variable, you can also see differences between groups that are just due to individual differences or pre-existing differences. Now you can minimize this by randomizing the people in your study to different groups to reduce the amount of sampling error, but individual differences can still get in the way, especially if you don't randomly assign participants to conditions. So for example, in the pain study that I've been kind of mentioning, let's say that participants in the morphine group were recruited from a back pain clinic and participants from the fentanyl group were recruited from an arthritis clinic. Well, regardless of the difference in effectiveness of the drugs, there's already pre-existing differences in pain levels, right? So the pain being experienced by people with back pain is probably different than the pain being experienced from people in the arthritis clinic. So you may observe differences in pain between the groups after you manipulate the drug, but that difference may not be due to the drug. It may just be due to differences in the type of pain they're experiencing. So again, if you randomize your selection to groups, you should have, a nice distribution of all those individual differences across those groups. Now, between groups differences can also be due to experimental error. So maybe the researcher unintentionally treated groups differently, or maybe there was just some poor methodology that led to those observed differences in the dependent variable across the different levels of your independent variable. So for example, in the pain study, maybe the experimenter, the one who administers the medication and guides participants through tasks and collects data. So maybe this research involves having somebody do strenuous activities and then measuring how long they can do those activities before the pain is too much. So you'd be like operationalizing pain based on how long they can do those activities. So maybe that researcher, the experimenter, isn't really giving everybody in the study the same treatment. So maybe he's going easier on some people than he is on others, and that's resulting in differences in how long they can do the activities. So to prevent this experimental error, the researcher should not know which medication is being administered and which groups participants belong to. Also, the participants should not know which groups they belong to, especially the control group. So have you ever heard of double-blind studies, right? So double-blind studies refer to trying to control for experimental error by not really cluing the experimenter or the participants into which groups they're in. Now, of course, there's another experimenter who's not really interacting with the patients who keeps track of these things so that they can do the statistical analysis later. So here's the problem with not doing a double-blind study, especially in a pain example. If the experimenter knows which groups people are in, which drugs they're getting, they may treat the groups differently. So they may feel bad for the people in the control groups. They may go easy on them, and then it may look like, oh, wow, they actually, were able to do these activities longer. Maybe the drugs don't have any effect. But it's not because of the drug, it's because the experimenter went easy on them. So you can have misleading differences due to the experimenter knowing which groups they're in. If the participant knows, then you could have some like psychosomatic symptoms that arise, or participants may be resentful if they're in the control group. So they might know they're getting a sugar pill, they might be upset, and they might try to contaminate your results. So double-blind studies help minimize experimental error. But between group differences, the differences, for instance, you would look at between the mean for group 1, the mean for group 2, and the mean for group 3, that can be due to the independent variable. It can be due to pre-existing individual differences, or it could be due to error in the study. Now, within groups differences or within levels variability can only be due to error, right? So 1 and 2, or 2 and 3 here, right? Individual differences or experimental error. So the individual differences, scores for participants within a single treatment condition are not usually identical, because you have different individuals that have pre-existing differences in the dependent variable. And keep in mind that these differences within groups have nothing to do with the independent variable. We're just looking at differences within the group that receive the same level of the independent variable. So we know that differences are either due to individual differences or experimental error. So again, unintentionally treating individual participants within the groups differently. Now, the F statistic provides a really nice way to isolate the treatment effect or the differences due to the independent variable from the differences due to error. So if you think about the math behind this, we're looking at the differences between divided by the differences within. So the numerator and denominator both include differences due to error, right? Individual differences or experimental error. But the numerator includes the independent variable as well. So basically, you're taking error plus the independent variable divided by error. And the error in the numerator and denominator cancel each other out, and then you're kind of left with the differences due to the independent variable. So if there's no differences between groups that's due to the independent variable, then you'll have a 0 for the differences due to the treatment effect, and you'll simply be left with the differences due to error divided by the differences due to error. And you'll be left with an F statistic of 1, right? Anything divided by itself is 1. Now, if there's just no differences between groups whatsoever, then you would get an F statistic of 0. So keeping that in mind, let's take a look at the F distribution. So in ANOVA, the F statistic compares the between groups variability or differences to the within groups variability to see if the between groups variability exceeds the within groups variability. So again, we are hoping that there's a lot of differences due to the independent variable, so our numerator, which includes the independent variable differences, is going to be larger than our denominator. But if there's no variability between the groups that's due to the independent variable, our F statistic equals 1, right? Because there's no differences due to the independent variable, we have error over error. So the F distribution represents the null hypothesis, and under the null hypothesis, the independent variable has no effect. So the bulk of F statistics under the null fall at a value of 1. Differences are only due to error. We would fail to reject the null and say there is no significant differences. And then remember, if there's no difference across the groups, be it due to error or be it due to the independent variable, which is actually a really rare occurrence, then your F statistic would equal 0. And see, even under the null, that's a very low frequency occurrence. So the F distribution is based on variability, which is never negative. Remember, when you were calculating variance and standard deviation, you never had a negative value. So if you look at the F distribution, there is no negative side of the distribution. It's a positively skewed distribution where under the null hypothesis, most F's fall under 1 because there's no difference due to the independent variable. So for F, we're only concerned with the tail to the right for the critical region. So this is going to be a lot easier because before, in step 2, you needed to draw your critical region to determine if your statistic actually fell in it, right? From step 3 to then reject the null or fail to reject the null. Well, here, we just want to see in step 3, is the F that we calculate larger than the F critical? Because again, we're only concerned with the tail to the right for the critical region. So as F gets larger, that means that the differences between the groups who do vary with respect to the independent variable exceed the differences within the groups who do not vary with respect to the independent variable. So ANOVAs are never used for directional hypotheses. There's never a one-tailed, well, it's always a one-tailed test, but it's not because we're expecting a higher or a lower F value. F's always going to be positive. So ANOVAs are not used for directional hypotheses. Again, F will always be positive because it's computed from variances, which are always positive values, and extreme F values will always fall on the extreme right end of the distribution. And then again, keep in mind, ANOVAs are an omnibus test that indicates whether or not significant differences exist between at least one pair of groups. It's the post hoc analysis that gets into the nitty-gritty of those findings, so which groups are significantly higher or lower. So that gets into the more refined interpretation of your results. But the main thing I want you to take away from this is that you're never going to have a negative F value. Under the null hypothesis, the independent variable has no effect, and most of the F values fall at a 1. And then as F increases, that means that there's more differences observed in your dependent variable that's due to the independent variable. Okay, so here's some statistical notation for you. I've already been talking about factors and levels. So factor is just another word for the independent variable or quasi-independent variable. Then your level represents the different levels of your independent variable, the different conditions in your study, the different groups in your study. So that the independent variable forms the basis for what you're manipulating, and then the levels represent the different groups in your study. Then K is the symbol for the number of levels. So when you see what is K, you're just being asked how many groups are in your study. Uppercase T represents the sum of X for a single level. So just for one group, what do all their scores add up to? Lowercase n is still the sample size, but it's the sample size for one level. And uppercase N capital N, is the sample size for the entire study. So the sample size for each level added together. And then G stands for the sum of X for the entire study, the grand total, sum of all scores for all levels. So T and lowercase n are notation. So T is sum of X, N is the sample size for a single level. Capital N and G represent the sample size for the whole study and the sum of X for the whole study, and then K is the number of levels. And I give you that notation because you'll see these formulas here include those values. Now, looking at this may seem intimidating, but I assure you that students struggle a lot less with the calculations for ANOVA than they do with the calculations for the T statistic. So I'm going to do lots of examples, but I just kind of want to break down the calculations in this table for you before I start doing calculations. So this is all step 3 of the hypothesis test, doing those calculations. So the first thing that you can do is add the sum of squares for each treatment or each level or each condition, right? You add the sum of squares for all your groups. That gives you your sum of squares within, or the overall differences due to error. Then you can find your sum of squares total, and I'm skipping this for now for a reason, by using something that looks very similar to the sum of squares formula you've been using all along, right? We've got the sum of x squared, which is basically taking every single score in your sample, every single value in your data set, squaring it and adding it together, minus g squared, which is just taking all those scores and adding them together and then squaring it, divided by the total sample size for the entire study. So again, very similar to the sum of squares you've been working with all along. So once you find these two values, you can just take this value minus this value to get the sum of squares between. And that's much simpler than doing this formula right here. So you can always test this using this formula. And for this one, you would take the sum of, if you have 3 different groups, you're going to have 3 of these. So the sum for group 1 squared minus the sample size for group 1 plus the sum for group 2 squared divided by the sample size for group 2 plus the sum for group 3 squared divided by the sample size for group 3. And then you add all those together, sum, and subtract the sum of all the score squared divided by the sample size for the entire study. This will give you the same thing as this, and trust me, it's much easier to find sum of squares within, especially if you're given the sum of squares for each group, and to find sum of squares total, than it is to do this. Just find the difference there. So first calculate sum of squares total, then calculate sum of squares within, and then calculate the sum of squares between using sum of squares total and sum of squares within. And this just represents all the differences due to error and the independent variable. Then you find your degrees of freedom for between, within, and then total. Degrees of freedom between, you just take the number of groups and subtract 1. So if you had 3 groups, degrees of freedom between would be 2. 3 minus 1 is 2. Degrees of freedom within, you take the sample size for the entire study and subtract the number of groups or number of levels or number of conditions, however you want to say it. So if our sample size was 20 and we had 3 groups, our sum of squares within would be 17. 20 minus 3. Then for total, you take the sample size for the entire study and subtract 1. So if our sample size was 20 for the entire study, we would have 20 minus 1 is 19. And guess what? Sum of squares, or degrees of freedom between plus degrees of freedom within equals degrees of freedom total. So you can check your work and make sure that that pans out and you didn't do anything wrong. Then, honestly, once you find the sum of squares and the degrees of freedom, it's pretty simple because the mean squared is essentially variance. So MS stands for mean squared, and mean squared is, again, just another term for the variance. Because remember, when you calculate variance, you take the sum of squares, divide by the degrees of freedom. So for mean squared between, you take the sum of squares between, divided by the degrees of freedom. Mean squares within, take the sum of squares within, divided by the degrees of freedom within. So essentially, once you find the sum of squares and degrees of freedom, you can just go this divided by this gives you this. And then this divided by this gives you this. And then for F, this divided by this gives you F, right? Mean squared between divided by mean squares within gives you the F statistic. So this is the variance between, the variance that's due to the independent variable and error, divided by the variance within, the variance that's just due to error. And the hope is that the differences due to the independent variable far exceed the differences due to error, and you have a large F statistic, which falls way off to the right of the F distribution, past your critical value, and you can reject the null and rejoice in your significance. Okay, so here are the other steps of the hypothesis test for ANOVA. And guess what? These are the same 4 steps that you've been doing all along for z-tests and t-tests. So step 1, state your hypothesis. Now for the ANOVA, remember this is an omnibus test. We're just saying is at least one of our means for one of our levels or groups or conditions significantly different from the rest. So that's your alternative. And you literally write out at least one mu is significantly different. And we say mu, not m, right? The population mean, because we don't really care about the sample. We just care about what the sample tells us about the population. So if we reject the null in favor of the alternative, we are saying that we think that in the population, there would be at least one group that's significantly different with regards to the dependent variable because of the independent variable. Okay. Then our null, you simply have mu1 equals mu2 equals mu3 equals however many mu's you're looking at, right? However many different groups you're looking at. So it depends on the number of levels. So if you have 2 levels, you can simply say mu1 equals mu2. If you have 3, mu1 equals mu2 equals mu3. If you have 4 different groups, mu1 equals mu2 equals mu3 equals mu4. However many groups you have, you're going to have mu's there. Now, for the alternative, if you love stating it in symbols, let's say we had 3 different groups. You could say mu1 doesn't equal mu2, or mu1 doesn't equal mu3, or mu2 doesn't equal mu3, or mu1 doesn't equal mu2 doesn't equal mu3. That's a lot of pain and suffering. You can literally just say at least one mu is significantly different and we're good to go. All right, step 2. Finding the critical value to determine how large your F observed needs to be to reject the null hypothesis, say that at least one mu is significantly different. Now, the hard part about this is finding your F critical is using dF numerator and dF denominator. So let me go ahead and show you the table. Okay, so here's the table. And so we are going to go to keep on going. Not F max, but just the F distribution. So you see degrees of freedom denominator and degrees of freedom numerator. So, and I have it summarized here in the slides. Degrees of freedom numerator refers to degrees of freedom between, because that is the numerator of your F statistic, right? Between groups variance. Degrees of freedom denominator refers to degrees of freedom within, because that is what we're looking for in F, right? The denominator of F is the variance within. So degrees of freedom numerator is k minus 1. Degrees of freedom denominator is n minus k. So I usually do step 3 of my hypothesis test first so I can get my degrees of freedom, and then I go back, state my hypothesis in step 1, and then find my critical value in step 2 using my degrees of freedom that I already calculated. And just as a side note, when you do step 3, make sure that you place your final values into a source table like you see here. So you'll have your values written in a table like this, just to keep everything organized. So step 3, you calculate the F statistic. I already showed you kind of how to do that. We'll do examples in the next set of lecture slides. Then, step 4, you compare what you calculated in step 3 to the critical region in step 2. If you have an F value that you calculated that exceeds the F critical, you can reject the null hypothesis and say at least one group is significantly different. Then you would calculate the effect size and do a Tukey's post hoc analysis to figure out which groups are significantly different specifically. If the F that you calculate in step 3 does not exceed the F critical in step 2, you fail to reject the null. Then you say that no groups are significantly different, right? They're all statistically equivalent. We don't think that in the population they would be different. So when you fail to reject the null, then you don't need to calculate Tukey's HSD. You don't really care which groups are significantly different because you already know none of them are. And who cares about effect size if your findings aren't significant? If you don't have statistical significance, we don't really care about practical significance. And just another note, when you state your conclusion, be sure that the conclusion reflects the context of the original research question. You wouldn't just put no groups are significantly different. You would frame it in the context of what we're actually looking at. So if we were doing the pain example, you would say there is no difference in pain intensity based on taking morphine, fentanyl, or being in the control group. For example. All right, effect size. So effect size is called eta squared. This is a Greek eta, and there's a little squared. And it's equal to the sum of squares between divided by the sum of squares total. So you'll simply go to your source table, take this divided by this to get your effect size. Now the cool thing about eta squared is that the interpretation is the exact same as for r squared. It's still telling you the proportion of differences or the proportion of variance in the dependent variable that can be accounted for by the independent variable. Or in other words, the amount of differences in what you measured that can be accounted for by what you manipulated. And then the evaluation of the effect size is the same as r squared. So if it's around 0.01, small effect, 0.09, medium effect, 0.25, large effect, and then above 0.25, we would call that a very large effect. And I love r squared because it can only range between 0 and 1. And you can turn it into a percent. So like if you have an effect size that was 0.25, you could say 25% of all the differences in what I measured, my dependent variable, can be accounted for by what I manipulated, my independent variable. So it's very interpretable and it's nice. Then the next follow-up calculation, if ANOVA is significant, would be effect size. Or not effect size, but there's effect size. But then it would be Tukey's HSD, right? So the way that you find Tukey's HSD, the honestly significant difference, is you go to a table and you find this value for Q. So for the Q table, you need to know what degrees of freedom error is. And remember, the within portion of your F statistic is the differences due to error, right? Either individual differences or experimenter error. So DF error is referring to degrees of freedom within, which is also the same as saying degrees of freedom denominator if you're looking at the F table. So you'll see when you look at the Q table, and it's actually, let's see, there's the F distribution. Oh, there's Q, right? There it is. The studentized range statistic. So you'll see that you're looking for degrees of freedom error, which is the same as degrees of freedom within. You'll just find that here. And then K, the number of treatments, or the number of conditions, or the number of groups, or the number of levels. You'll find that here. And you'll find where those two numbers meet. Now for both the Q and the F table, the value in bold represents the alpha level of 0.01, so the extreme 1% of the distribution. And then the value in light face represents an alpha level of 0.05, or the extreme 5% of the distribution. Okay, so you'll find Q in the table, and then you'll multiply that by the square root of your mean squares within divided by n. So again, the source table is important because you have to keep all these calculations straight, right? So you'll go find mean squares within to plug it into your formula for Tukey's HSD, divide that by n. Now n is the sample size for a single group. So if you have 4 groups and there's 5 people in each group, your sample size isn't going to be 20 here, it's going to be 5. And so that being said, you can only do Tukey's HSD by hand when you have an equal sample size across your groups. So for all the examples we do, each group's going to have the same sample size. And that's actually a good practice for ANOVA anyway, because your results are more reliable when you have about the same sample size in each group. Now what Tukey's HSD tells you, once you take Q from the table and multiply it by the square root of the mean squares within divided by n, this tells you the mean difference necessary between two groups to be significant. So you'll find Tukey's HSD, and then you'll take every single mean difference. So if you had 3 groups, for instance, you would take the difference between group 1 and group 2, group 1 and group 3, and group 2 and group 3. And then you'd compare those mean differences to Tukey's HSD. And all of those mean differences that are greater than Tukey's HSD would tell you that there's actually a significant difference between those 2 groups that were used to calculate that mean difference. So right now it seems kind of weird and abstract, but the next video will show you 2 examples and I'll do all of these things for you. And before I end this conceptual part of the lecture, here's something that hopefully makes you laugh, some ANOVA humor. It was hard to find, but there's some ANOVA humor for you. So I hope that you feel prepared to look at examples now and that you understand what the F statistic tells you and how to look at Tukey's HSD to determine which groups are significantly different.